Forget about the derivation process. Do you know the physical meaning of this formula? What is R? Don't get lost. What is R? Great. If you know small r, what can you know? For example, the percentage of power reflected back in this three-layer structure. Okay. In theory, you need to do a lot of math, but after that, after you have equation 17, you can skip all the derivation. Just use this formula with all the parameters, such as the three refractive indexes, the thickness of the layer, N1 layer. Using equation 17, you can know coefficient R. And if you have small r, after taking absolute square, you can know the reflectance, the percentage of power getting reflected back. Okay? But in this section, what we are really interested in is not the reflectance, but the phase contribution. Although reflectance is more intuitive, you can sense the meaning of reflectance easily, percentage of reflected power. But here we are more interested in the phase term, because small r is a complex number. You have magnitude, but you have phase as well. If you generalize the one-layer structure to multi-layer structure, it could be like this. Previously, we have N1 only. Now you have N1, N2, all the way to NP. Say you have P layers. And each layer can have its own refractive index and its own thickness. Very arbitrary, okay? Then the total fields of the first layer and the last layers are related by a matrix equation still, okay? First layer, first interface is here, okay, between Ni and N1. Total fields are E1 and H1. Last interface is here between NP and NS. NS is the substrate. Total fields are E sub P plus 1 and H sub P plus 1. And you can skip all the tedious mathematics happening in between. Just look at the initial and the final interface. You can have this matrix equation and the relation between E1, H1 and EP plus 1, HP plus 1. The question is, what is the matrix M? It's still a 2 by 2 matrix, and actually it's the multiplication of P matrices. For each layer, you have one matrix, as we did before. You repeat the process. For each layer, you have one matrix. Total matrix is just the joint product of all the matrices. Okay? Do you know why? 并不是说一层有个矩阵，那总矩阵就自动会变连层哦，不是，你要知道为什么？为什么？根据定义嘛，之前的 matrix 是说这个 phase 跟这个 interface 之间的关系。那接着再用一次，第二个 matrix 就是 relate 这个总电场总磁场跟这个总电场总磁场，那跟上一个 matrix 有相同的地方嘛，所以你可以连成是这样来的。OK。And in this way, you can calculate the reflectivity or reflection coefficient small r by the same equation, equation 17. Okay? Because in equation 17, these parameters M11, M21, and so forth are here. The 4 elements of the total matrix. So whenever you know the total matrix, you know these 4 numbers, and the equation 17 works. No matter it's single layer or P layers, doesn't matter. Okay? one example, quarter wave stake. Okay. Here we have n pairs of layers. One pair 1 consisting of 2 layers, index n1, index n2, and the thickness are fixed. D1 equals lambda 0 over 4n1. D2 equals lambda 0 over 4n2. Okay, so whenever you determine the index, you determine the thickness simultaneously. The thickness, according to this formula, is a quarter of the wavelength in that material. Okay. 对不对？你在 N1 这个材料，你的等效波长是 lambda 0除 N1 哦。到第二种材料里面，等效波长变 lambda 0除 N2， 那等效波长会变的。那我们的厚度呢，都是1/4波长，但是是1/4等效波长，所以这两层的实际厚度是不太一样的，因为 index 不一样。Okay, but why do we need these conditions? Because in this way, the phase shift in each layer is always 90 degrees, pi over 2. If the delta equals pi over 2, you can check the matrix formula. You can see 2 elements should be 0. And the other 2 are purely imaginary. And the magnitude are in reverse with each other. Okay, that's the characteristics you can have by setting the phase shift equals 90 degrees. Okay, and in this case, matrix multiplication becomes extremely trivial. 你连乘不是问题，为什么？你连乘完以后会变成这个结果。你把这两个一连乘完，就会变成这样子的一个 diagonal matrix. Now, 2 elements are 0. The other 2 are minus real number. Okay? And the real number is defined by the index ratio, n2 over n1. So you can control the 2 indexes to control the alpha parameter, to control the matrix. Okay? But we have more than one pair. This pair 1, pair 2, pair n. We have n pairs. So the total matrix is simply the multiplication of n same matrix, right? It's a special case, and you have this result. 这是一个很简单计算的，因为是 diagonal matrix， 去连乘就很容易，就把它换成 n 次方就好了。Okay? And in this case, using equation 17, you can quickly calculate the reflectivity, small r, which is governed by equation 19. Okay? So if you satisfy the quarter wave thickness condition, you can have equation 19. The reflection coefficient small r, it can be easily calculated by this formula. And you can make small r a very big number close to 1 or a very small number close to 0 by controlling alpha and number of pairs, big N. You have 2 parameters. Okay? If small r is close to 0, what does this mean? Remember, small r is here. If r is close to 0, that means transparent, almost no reflection, right? So this is anti-reflection coating. If you make small r with a magnitude close to 1, it means reflector, not anti-reflection coating. Okay? 所以同样的结构呢，你只要适当的去控制这个 big N 跟 index contrast alpha, you can make it either anti-reflection or high reflector. Okay, and in our case, we are more interested in high reflector. And this structure is usually referred to DBR, distributed Brock reflector， 一个多层膜结构就可以设计出一个高反射率的反射器。Okay. Any question? Equation 19 does not hold if wavelength is not equal to the Brock wavelength. Remember, here, this perfect formula only works for a single wavelength, right? Because if your working wavelength is apart from the Brock wavelength, this condition is violated, no longer 90 degrees. Your matrix, 2 by 2 matrix, you have 4 non-zero elements. So this one will not work, this one will not work, this one will not work. Okay? 所以其实只对一个波长是这么完美的，其他波长怎么办？ Other than that, you have to numerically calculate the complex reflection coefficient. But you have computer, it's not a big deal now. Okay? And you can change the working frequency or wavelength, and you can calculate all the corresponding reflectivity or reflection coefficient. Then you have the complex spectrum for the reflectivity, right? If you take absolute square, you got reflectance spectrum. As I mentioned, it means for different colors, the percentage of reflected power changes. That's the meaning of reflectance spectrum. Okay. But if you look at the phase of your reflectivity spectrum, and with a second order derivative, taking a factor of 1/2, you actually have the quadratic spectral phase coefficient. And that is the GDD parameter, right? So now you know why we need to spend so much effort in the analysis of multilayer structure. Because the multilayer structure not only gives you a reflectance spectrum, but also gives you group delay dispersion spectrum, right? And if you want to compress your pulse, chirp pulse, you need certain amount of GDD, and then maybe, we don't know yet, but maybe you can use a multilayer structure to achieve the same goal instead of using a grating pair, right? 所以完全不一样的逻辑哦。Grating pair 用到 angular dispersion， 不同的 color 走不同的角度，然后有不同的 path length， 我就可以制造 GDD dispersion。这里有没有 grating？ 没有，这是 multilayer structure，no angular dispersion at all。But it can still create dispersion. The idea is you have to prepare frequency-dependent phase shift. If you can do that after second-order derivative, you got GDD. Okay, that's the central idea. Using a multilayer structure to prepare frequency-dependent phase shift. Although no physical length, physical path length difference. Okay. So you can regard a DBR an interference-induced dispersion device. 所以 grating pair 是基于 angular dispersion 来产生 spectral phase modulation. A multilayer structure or DBR 是 based on interference 干涉，完全不一样，但是也可以产生 dispersion. However, things are not so perfect as we expect. Let's check out the reflectance spectrum. First, reflectance spectrum is defined as absolute square of reflectivity spectrum. Okay? And it is large and flat over this frequency range. Okay? So if you look at the solid curve in this figure, this is your reflection spectrum, okay? Vertical axis is reflectance up to 100%. Horizontal axis is normalized angular frequency, omega over omega b, okay? You can see you have nearly 100% reflectivity over a spectral range determined by parameter delta. Delta is defined here. It is the normalized reflection bandwidth 很明显嘛 ，delta 的意思就是频宽，只是它是归一化过的频宽它没有物理单位。And your normalized bandwidth delta is determined by this formula: 4 times arc sine of rho divided by pi constant. And the rho is index contrast. The formula is here. N2 minus N1 parentheses over N2 plus N1 parentheses. 这就是一个你不是有那个 N1 N2 N1 N2 的结构吗？这个折射率的对比度就叫做 rho 用 rho 可以决定 delta， 也就是决定这个 bandwidth。Okay. So let's check the range of delta. Okay. Because delta depends on rho, so let's check the range of rho first. What is the, for example, the minimum rho you can have? 0, right? When n1 equals n2, you have 0 rho. What is n1 equals n2? 你就没有什么 pair 了嘛，因为两个就变同一个介质啊。In that extreme case, rho equals 0. What is arc sine of rho? Still 0. So you have delta equals 0. That means no bandwidth. 那意思就是什么？当你没有 n1 n2 了，其实 merge 在一起，没有这个东西，完全不见了。Okay. And what is the maximum rho you can have? 1. 1 is maximum. Suppose the n1 equals 0, you have n2 minus 0, n2 plus 0, you have biggest rho. And in that case, arc sine of 1 equals pi over 2. 4 times pi over 2 over pi, you got 2. That's the maximum bandwidth you can have. And if this width is 2, that means the center is always 1. So you have from 0 to 2. That's the maximum bandwidth. It's reasonable because you cannot have negative. 最宽就是2. And in this specific case, delta is maybe 0.3 or 0.4. Okay? But this formula shows the refraction bandwidth depends on index contrast. The larger the contrast, the broader the reflection bandwidth. 所以你拿一个 dBr 来当反射器，你希望它工作的频宽越大，你要做的事就是 n1 n2 的折射率差要够大，对比度大，这个频宽就会大。Okay? But as I mentioned, reflectance spectrum is out of our interest. We are more interested in the phase spectrum. Okay? So if you plot the phase term, you got the dashed curve. Do you know how to get the dashed curve? As I mentioned, the formula, equation 19, only applies to single wavelengths, the Bragg wavelengths. If you want to plot this curve, you have to calculate many different wavelengths. So you need numerical simulation. Okay, there is no simple formula. But if you do that, for each refraction coefficient small r, you take the phase term, and point by point, you can plot the dashed curve. And the shape is pretty strange, right? Very sharp here, very flat in between, very sharp again. Okay. Sorry, this is side 2. So that is not directly from the face, but after second order derivative. 说明详细一点哈，你把小 r 算出来，取了 face， 你不会直接得到它哦。你取完之后还要做2阶微分才会得到它。好 ，anyway， 你可以用程式把这个画出来。就你发现的是什么 ？In the high reflection band, meaning here, when reflectance is close to 100%, the corresponding GDD is almost 0. Okay, unfortunately, right? 0 GDD does not help in post-compression, right? And you do have anomalous dispersion here. Your side 2 is positive. You do have normal dispersion here. Your side 2 is negative. However, in these regions, your reflectance drop rapidly. That means if you want to access normal dispersion, you will suffer strong loss. If you want to access anomalous dispersion, you will suffer from loss as well. Okay. So in practice, DBR structure is of practical use in post-compression. 因为它有效率的地方就没有色散，它没效率的地方才有色散。所以你为了要用色散，你就要损失很大的 power. It's not a good idea. Okay. So, what's the solution? We spent so much effort, and we were happy to find one solution. We have a new device. Creating dispersion by interference, multi-layer structure, but it turns out that does not work. Okay. So people are very smart, driven by need. If you have some need, you will have invention. You can generalize DBR to simple chirped mirrors, longitudinally varying the period. Okay, so I illustrate the idea like this figure. This is your substrate. Standard DBR, you have N1, N2, N1, N2 all the way. Okay, and the period is fixed. But here, the period is chirped, right? So you have large period here, smaller and smaller. Okay, and if your incident spin is from the right-hand side, okay, this means your incident spin is a chirped pulse. Red part first, blue part later. So this is an upchirp pulse, right? Red leads blue. It's upchirp pulse. Okay, and you can imagine the blue part will be reflected here because blue part will be reflected at a shorter period range. 我们知道那个布拉格反射器反射的波长跟周期是相关的，基本上是越短波长就会被越短的周期反射。那在这个结构里面，短周期出现在前面，所以 blue part 走到这里就被弹回来 ，green part 走深一点 ，red part 走最深才回来。So what happens after the incident spin get reflected? Your chirp is de-chirped, suppressed at least, right? 领先的呢要走远一点嘛，落后的走近一点啊，出来不就大家都挤在一起？啊，这就是 post compression. This structure provides anomalous dispersion, right? And besides, you have broadened the reflection bandwidth. Not like standard DBR. Now, if you highly chirped structure, you can cover more and more wavelength components, right? 就是你的频宽即使很大，你反正只要在整个结构里面都做出它看得到的反射周期就行了，就通通可以吃下来，对不对？就不受限于刚刚那一个 dBr 的公式啊。So you can have broadened the refraction bandwidth by simple chirp mirrors, and you can have wavelength dependent group delay tau g, which means group delay dispersion. Okay. So this is one example. Horizontal axis is the wavelength from short to long wavelength, from blue to red. And the group delay is a monotonically increasing function. So just like this, this picture, you have anomalous dispersion effective. Okay? Can you have normal dispersion? Quite easy, right? Just reverse the chirping. Long period first, short period later. You have normal dispersion. So not like the grating pair. You need the 4F configuration to create normal dispersion. But in chirp mirror, it's quite easy. Just reverse the order.